Russian appraiser for this year. And he has been just very close by, but as you know, coming from technical. So we're very happy that we have him here. He was a student, he was a graduate student when I went to college in my first year. And he was in the same university, so great to see him again.
Thank you. Thank you for inviting me. Okay, today I'm going to talk about the gravitational microlensing and its application in understanding the structure of our galaxy. I will introduce the EROS data and how to use it for studying the galactic structure. And here are my collaborator from CNRS, from San Antonio, and from the Mindset collaboration. We are using Danish telescope at Paczynski. So where is Sharif University? It's here in Tehran. We have, this is our physics department, and we have about 35 faculty here, and 2 of them, me and Reza Mansur, is working in astronomy and cosmology. We have another institute for this is a picture I took from one of my friends taken a few days ago in Tehran, and this is astronomy school at IIT. So there are about 10 people working here. 5 of them are postdoc, and the rest are the member of this school.
Do you mean it's known in Tehran?
So yeah. What's gravitational lensing? It's we know that it's a bending of the light when it crosses near a massive object. It can be a planet or star or galaxy. So the observation effect is that we observe the real position of the star. Here we see the position of the star here. So we can see this effect in the sky. So this is a experiment is done in the laboratory. So if you cut the bottom of wine glass, it looks like the gravitational lensing. So if you just pass a ball behind this glass, okay, you see that the 2 images appear here, and we have an Einstein ring, and then again 2 images here. So exactly same things happening in the universe. So if we look at the cluster of galaxies, so these are the lens cluster, and then these arcs are the images from the background galaxies. So exactly we can see these images in the sky. And this is another example that we see that there was a almost spherical symmetric lens here, and we see 2 images produced by the background galaxy. So I'm going to focus on the gravitational microlensing and give a brief story of the microlensing. So first paper or first work appeared by Einstein in 1936. He studied the gravitational lensing of star by another star inside the galaxy, and the conclusion of this paper, his work, was that there is no great chance of observing this phenomenon in the galaxy. The reason is that if you calculate the probability, it's very low. 1 year later, Zuki told that we can observe gravitational lensing if we use galaxies as a source and other galaxy as a lens. Okay? Then few decades later, it has been observed. But in the gravitational lensing of a star by another star, there was Paczynski that in 1986 told that we can observe gravitational microlensing with the telescope at that time, and also with CCD. And he proposed using gravitational lensing of a star by another star for studying the kind of dark matter, which is called MACHOS, massive compact massive astrophysical compact halo objects in the galactic halo, because people suppose that maybe the dark matter is made by these MACHOs. In 1993, the first microlensing has been observed. So this is the light curve of the background star, which is magnified during the lensing. So I'll discuss more detail later. And then in 2001, two main groups for detecting MACHOs, EROS and MACHO collaboration, conclude that there is no MACHOs in the halo. So we can just delete this candidate from the list of the dark matters in the galactic halo. So there is no MACHO in the galactic halo, in the galactic halo. And but later, after 2001, people used gravitational microlensing for astrophysical studies. For instance, they used the gravitational microlensing for detecting extrasolar planets. So in 1991, Mao and Paczynski proposed using the gravitational microlensing for detecting the extrasolar planets. I will discuss it in detail. Okay, what's gravitational lensing? In the gravitational lensing, we have three elements of observer, lens, and source. In the absence of this lens, this is the light track that comes to the observer. But if we put the lens here, then this light will bend, and then observer can see this, but observer can see another light ray coming from this side or from this side. So we know that the deflection angle from the Schwarzschild metric. Okay, so just using a simple geometry here, we can find the position of the image as a function of position of the source, and also the impact parameter. So we can write the lens equation and solve for this, and we know the position of image, and we can guess that where's the source and what's the size of the lens, or what's the mass of the lens. So, and also we can get the lens equation from the Fermat principle, Fermat potential. So the Fermat potential made by two terms. First term is geometrical term. It's the difference that light goes from this way compared to this way. And the second term is the Shapiro effect. The flux, or the GR effect, that flux moves slower near to the lens compared to the, okay, here goes very slower. And then if we add these two terms here, then we can write this Fermat principle like this. And then the saddle point and minimum maximum gives us the position of the lens, position of the image as a function of position of source. So this is the lens equation. And then we can find, so this is this equation is a map from the source plane to the image plane. And if we have an element here, we can find this differential element in the image plane. So if we calculate the Jacobian of this transformation, this gives us how much the area is getting bigger. So this Jacobian gives us the extra energy that comes to us, or the fraction of the energy with respect to the case that we compare the source. So this fraction of these two areas will give us the amount of magnification. Okay? So
what is beta and what is theta?
Sorry?
What is beta and what is theta?
Beta is the position of source, and theta is the position of image. Okay? So, so in the star-star lensing, that I'm going to use the term of microlensing because in this case, the difference, the angular separation between the images is micro arcsecond. So, unlike the cosmological scale, the microlensing, which is produced by a star and by another star, is a dynamical effect. It's not a static lensing like in the cosmological scale. So we can see the ongoing lensing in our lifetime. It takes about 1 month inside the galaxy. So we can see that the star come across our line of sight and go away, and we can see the lensing effect. So, but the problem is that the probability of lensing by star by another star or microlensing effect is very low. It's 1 per million. So this is what's happening in the lensing in the microlensing or in a spherical lens, spherical symmetric lens. So this is our source, and when we put the lens here, then we receive these 2 light bundles from 2 sides. And the lensing effect is that it converges the light beams to the observer and the more energy comes to the observer. So it increases the intensity of the background star. So the ratio of these 2 areas with respect to this area gives the amount of magnification of the light. So since this is a dynamical effect, since the lens is moving compared to the source, this ratio will change by time. Okay? So if you look at the light, if you look at the intensity of the source star, you see that it's increasing the peak and then comes to the baseline. And the magnification formula is very simple calculations done by Paczynski, and this is a function of 3 parameters. U0 is the time for the maximum peak, T is the transit time, and U0 is the height of the light curve. So if we have a light curve, we can fit the light curve in the Paczynski formula and get this 3 parameters. So the probability of detection is very low. So how we can calculate the probability of detection? So each lens has a characteristic length is called Einstein ring. So if we accumulate these areas and calculate the ratio of this area to the sky, this gives us the optical depth, or the probability that one of these rings cross the background star. And if we do this, we get 10 to minus 6. This probability is very low. That's why Einstein thought that there's no chance to detect this phenomenon. But thanks to the CC and the big telescopes, we can observe millions of stars in one shot. So this is one of the candidates for the lensing. Unfortunately, it's not here. It's not here. So there is the magnification of the background star. But here we can see this. This is a microlensed star that before there was very deep. Okay. So in the microlensing event, in the microlensing, the light of the background star amplifies and then comes down to the baseline. Since the gravitational microlensing, gravitational lensing is independent of the frequency, we should have the same amount of magnification in all wavelengths. So for instance, this is in the blue and this is in the red, and if we divide the amount of magnification, we get 1. So this is as a criterion tells us that this is really lensing or this is some variable star or some variable event in this star. So the gravitational lensing experiments use different filters and looked at background star at the same time in different filters, confirm that this is really a gravitational lens. So the EROS and MACHO collaboration and also OGLE collaboration, they observed the large Magellanic clouds. This is very smaller than the Milky Way. They observed the large stars in the large Magellanic cloud. They count the number of lensing effect, the number of lensing, and then say that, okay, if 100% of the halo is made by, if 100% of the dark matter halo is made of MACHOs, then we expect to see a given number of events. But they found very low events, and they put constraint on the fraction of halo that's made by the MACHOs as a function of the mass of the detector. So between 10 to minus 6 to 1 solar mass, so it's less than 20%. But they can put constraint on the very large masses, because large masses produce large Einstein ring, and it takes a long time, longer than the experiment time. So it takes longer than 10 years to cross the background star. So they put constraint in this range of the masses, and it's less than the 20%. So you can rule out the MACHOs as a candidate for the dark matter in the halo. So this is the conclusion from the gravitational microlensing, that they search dark matter MACHOs in the galactic halo. So there is no, we can rule out these MACHOs. There is no baryonic dark matter. Maybe there is no baryonic dark matter in the halo. It's called dark matter, warm dark matter, or maybe there is no dark matter, and you should change the gravity level.
But wait, so the idea is that you expect to have this massive dark matter MACHOs, and you didn't observe them, and then.
Okay, this is the number of expectation is not equal to number of observation. So we have microlensing events towards LMC, but they are due to the lensing in the LMC, in the galactic disk, or in the large Magellanic cloud itself. Okay, so.
But these MACHOs, do you assume one is a dark matter particle? Do you assume it's mass? I'm not familiar with what is this MACHO.
MACHO is a massive. It's a baryonic compact object.
Okay.
Like brown dwarf, black holes, white dwarfs. Okay. After 2001, there's another application for the gravitational lensing. For instance, for searching extrasolar planets. So there are different methods for the extrasolar planet detection, like radial velocity. In this case, the planet rotating around the parent star and moves this parent star with respect to center of mass, and then if we do spectroscopy, we can measure the radial velocity and say there is dark matter. There is transit method that if your system is edge on with respect to you, then we can measure, we can see the effect of the transit on the light group of the parent star, direct imaging, astrometry, and finally I'm going to talk about the microlensing. So each of these methods are sensitive to the parameter space of the mass and temperature of the planet, which is a function of distance from the parent star. For instance, the Doppler and transit are sensitive to the big mass and close by planets. And microlensing is sensitive to the planets far from the parent star, and even we can have a low mass. So by microlensing, you have a chance to detect Earth-like planets, extrasolar planets, and it's very interesting. Another advantage of the gravitational microlensing is that these methods are sensitive to the close-by planets. But by microlensing, you can find planets in future parts far from Earth. So this is also very interesting that you can find planets, for instance, in the bulge, in galactic bulge. So how the gravitational microlensing works for finding extrasolar planets? If you have two or multiple lenses in the lens plane, you can show that there are some areas in the lens plane called caustic line that the Jacobian of the transformation is 0. Means that mathematically, the magnification of the background star in this area, in this line, is infinite. Okay? So we can find this effect, for instance, if you look at the pool. So if you look at the bottom of the pool, you will see the very shiny line just moving. That's because you have some waves on the surface of the pool, and then when the light wave passes through the pool, you will have such a shape on the waveground, and this will produce a very high light intensity on the surface of the pool. Okay, so this phenomenon happens also in the gravitational lens. So when you have a binary lens, one of them is the parent star and the companion is a planet, it produces this caustic line. And when the background source crosses this caustic line, it produces very high magnification event. The high magnification magnifies the background light like this. So we have a magnification due to this parent star, and there another magnification due to this planet when the source crosses this caustic line. Okay. So this is the caustic line as a function of mass. Sorry, as a function of distance between the planet and parent star. And we see that sometimes we can make a very, like this, very narrow, long caustic lines. And in this case, we have more chance to detect a planet, because in this case, that the source, when source crossing this line, we have more probability to see the effect of the planet than here. And if they are very close, then the caustic line is negligible. So we can see just only the effect of the parent star. So the advantage of gravitational lensing is that we can see the planets very far from the parent star. So the size of this distance is about the Einstein radius. So Einstein radius is about the astronomical unit. So this means that we can see planets far from the astronomical unit, far from the astronomical unit, from the parent star.
And what is the Q?
Sorry, Q is the ratio of the mass ratio, the planet to the parent star. So we can see also the lensing, the effect of the planet when we put the source rotates around the source star. If you put the planet rotate around the source star, because the effect will be the moving the parent star with respect to their center of mass. And this will change, modifies the light curve, and then we expect to detect this effect on the light curve of the microlensing. So this method is completely different. We have different standard method for the extrasolar planet detection. So what's the conclusion from the microlensing is that up to now about 10 planet has been observed by the Microlensing method. And since we know the observational strategy, we can calculate the detection efficiency as a function of mass of the planet and distance of the planet from the parent star. So if we reconstruct the mass of the planets, then we can get the real distribution of the mass of the planets according to this efficiency function. So the result is the mass function for the planet. So this is the mass function of the planet from the Microlensing experiment. It shows that the Earth's mass type planets are very, very high. I mean, there are a lot of smaller planets compared to the, for instance, Jupiter mass planets. So this is very good news that we can find Earth-type planets around us. So this is and we can do this by other methods like Doppler effect, because Doppler effect is sensitive to the planets very near to the parent star. Okay. So finally, I'm going to talk about the understanding structure and dynamics of galaxy using gravitational microlensing. One of the famous experiments was EROS experiment. They observed not only towards the large magnetic cloud, they also had programmed to observe the center of galaxy and the spiral arm. They used the 1 meter telescope at ESO. This is a telescope. And this is the directions that they observed towards our galaxy. These 4 directions are towards the spiral arm, and this direction is towards center of galaxy. So if we look the direction of the observation from top, so these two directions cross the bulge of the galaxy, as you see here. So you can see also here that these two directions cross the bulge of the galaxy, and these two directions, gamma nor and theta nor, are far from the bulge. So our aim is to study the structure of the galaxy by the microlensing data. Okay, because it's sensitive to the distribution of the matter in the galaxy. It's sensitive to the velocity, dispersion velocity, and also the geometrical parameters of the galaxy. For instance, how this bulge, what's the bulge angle with respect to us. So these are the example of the microlensing data towards the spiral arm. You see the candidate for each case. So what we can get from each light curve is something like this. We can fit this light curve in the theoretical Paczynski theoretical model, and then get the time for the maximum magnification, amplitude, and also transit time. These two parameters has no physical meaning in them, but the transit time is a function of the relative velocity of the lens with respect to the background star. This is a function of mass of the lens, and also is a function of the distance of the lens and distance of the source. So all the physical information is inside this transit time. So this transit time is a function of what is the dispersion velocity of the stars in the disk, what is the mass function of the stars in the disk, and what is the distribution, spatial distribution in the disk with respect to us, with respect to the observer. So if we know the distribution of the Einstein crossing time, we can get some information about the galaxy. And other information is the rate of event. So we can count the data, the number of events, and then tell what is the rate of events. So to count the number of events, to count the real number of events, we know the detection efficiency of the telescope, the experiment. So this is a function of the transit time. So one of the important works that should be done in each experiment is finding this detection efficiency. It tells us how many percent of the fraction of the events that we can really observe in the experiment. So so if we know the number of the event, and then we can multiply this to 1 over detection efficiency, this gives us the real number of the microlensing events that happen, and from this number we can get a fraction of them. We can get the optical depth, and also actually we can have the color magnitude of the stars in each field. We can have the number of stars in each field. There are other informations that we can get from the experiment. Okay, so to compare the observation with the model, we can simulate the galaxy and compare it with the observation. So we need, for simulation, we need the matter distribution of the galaxy. We need the dynamics of the stars in the spiral arc. What is the distribution function for the velocity? We need the mass function. Okay. So if we put all these ingredients to the simulation, we can simulate the microlensing event, and finally we can compare with the observation. And also we need the luminosity function of the stars in the Milky Way, because the microlensing is sensitive to this parameter. If we have a bright stars, then we can see far stars. In this case, the optical depth increases, and then we have more lensing effect. And also it's a function of the dust distribution. So if we increase the amount of dust, that will deeper the luminosity, and then we can see far stars. So they will change the distribution of the Einstein crossing time, and also they will change the number of events. So to have the stellar population of Milky Way, we can take stars around the sun. The Hipparcos catalog can be used for making this synthetic stellar population of the disk. So Hipparcos catalog has about 100,000 stars. So it's complete up to 7.5 magnitude. And then we can make from this stars a complete sample, and then make our stellar distribution of our galaxy. So if we take stars up to 50 parsec around the sun, they are almost the distribution of stars almost spherical, and then for a given magnitude, okay, we can if we look at the very faint stars, that's complete to a given radius, and then we can obtain the number density of stars for a given magnitude. Okay, so this is the distribution of the Hipparcos data. This is complete. This is the complete. This is the distribution of stars with the average magnitude less than 7.5. They are less than the limiting magnitude of the Hipparcos satellite, and then we can normalize it to the volume and make the complete sample for magnitude and color. And this is the unbiased distribution of the color magnitude of stars in the galaxy. So we can make the So we have the stellar distribution of we have the stars, a complete set of stars, and then we can distribute it in the galaxy and make our simulated galaxy. Then, so we have this. We have our galaxy. We fill this to the stars, which is this. It looks like to the stars that taken from the Hipparchus catalog, taken from the around the sun, and then we put the telescope here and observe these stars. So if we use a ground-based telescope, a small telescope, so and compare it, the field, for instance, with the Hubble space image from the Hubble space telescope. And some of the stars, bright stars, we can see some of the bright stars here, but we miss some faint stars. So using the ground-based telescope, we will miss some of the faint stars. So we can obtain the detection probability for the stars as a function of their apparent magnitude. So we can use this in the simulation, and also we can use the distribution of the matter in the galaxy. So we fill the stars according to this distribution in the disk and the bulge with the corresponding dispersion velocities. And then finally we can observe them. This is simulated observation. So, and also we can include dust in the disk. So this is the color magnitude distribution from the simulation. Okay, so we have all the elements: stellar distribution, distribution of the matter, velocity, and dust. Then finally we can get the color magnitude distribution, and this is what's obtained from the observation.
So what are you assuming about the axial distribution of the stars, in angle 5 around the Milky Way?
So we use very simple model without considering this arms. Simple exponential model.
Exponential model.
Yeah.
So the lensing is dominated by relatively old stars that aren't concentrated with spiral arms. Don't worry about it.
Yeah, yes.
But at the center, there's a bar, so at some point that will lose axis in it.
We have just one. Okay, we have a smooth exponential model for this, and also we have a bar. We consider this bar, but not the spiral arms. Okay, now we want to generate the distribution of the Einstein crossing time, which has physical information in them. It has information from the mass function of the star, information from the spatial distribution of the matter, and also dispersion velocity of the star. So we can simulate the Micorlensing event, and then we have detection efficiency as a function of the Einstein crossing time. So for each direction, we can produce the expected Micorlensing event as a function of according to this model. So for the mass function, we have solved there. I explained the spatial distribution and also the dynamics of galaxy. Okay. And so this is the result. This is the solid line is the distribution of the source stars, and the dotted line is the distribution of the lens stars. So so this is the distribution of stars that we can observe in this simulation. Okay, in 4 directions. In these 2 directions of gamma splitting and beta splitting, we have the contribution from the bulge also, because you remember the line of sight thrust the bulge in these 2 directions. But for these 2 directions, they are far from the bulge. And one of the interesting results from the simulation is that if we look at the microlensing candidate in the color magnitude diagram, so this is a color magnitude diagram, 2 arms, this spiral arm, and these dots are the microlensing data. We project them in the color axis. We see that the population of the red stars are more than the distribution of the background stars. So the reason for this is that the bright stars, for the bright and distant stars, we have more optical depth. Okay? And the bright distant stars getting more redder and more redder due to scattering. So they're getting redder. So each star here gets dimmer and redder. Okay? So these stars are coming, in fact, they're coming from somewhere here. In fact, they are, in average, they are located far away from the other stars. So to show this effect, we can simulate the distribution of the stars. So this is the distribution of the stars in the field, and this is the distribution of the microlens stars. So we see that they are redder than the apparent distribution of the stars. So most of the microlens stars are located very far from the average distribution, average distance of other stars. And also we can put constraint on the parameters of the galaxy. For instance, phi is the angle of the bar with respect to the center of galaxy to the sun. So this is a galaxy. This is bar, and this is sun. So this angle is phi. So we can change this angle and find the best fit to the microlensing data, and it's about 25 degrees. It's compatible with the other observations like analysis from the true mass catalog. We can put constraint also on the speed of the dispersion velocity of the stars in the disk. So F dynamics is a factor that increases the speed of the dispersion velocity of the stars in the disk. The 1 is the standard model, and 1.5 is a factor that increases the speed of the dispersion velocity in the disk. So the best value is obtained around 1.5. So the speed tells us if we use a thin disk model, it's the highest dispersion velocity is more compatible with the microlensing data. So I skip this part and come back to it later. And this is a thick disk model. If we include also thick disk to the thin disk model, so this has also best fit if we have thick disk. So one is if we include a thick disk to the thin disk, and factor of 2 is if we have 2 times of thick disk matter distribution, and 3 is 3 times. So if we have a thick disk, then we will get better fit. So in the thick disk, we have a low thick disk which is included to the thin disk, but the difference with the thin disk is that it has more dispersion velocity. So the microlensing analysis shows that, okay, you can tell that the thin disk plus thick disk has a more compatibility with the observation, with the microlensing observation. So this is a mass function. We test this mass function. It shows that the standard mass function is defined here. So alpha is a factor that occurs in the exponent of the mass function.
So can you explain the finite to the one to the top right again?
This one. So this factor is the factor that increases the dispersion velocity of the stars in the disk.
Vertical?
No, all the dispersion. So we have a 3D, yes, in 3 directions. Okay? So 1 is the standard case. 0 is that we have no dispersion. Okay? 1 is the standard model, and 1.5 is that we multiply the dispersion velocity to 1.5. It's a factor. So, and also if we use a thick disk, in the thick disk, naturally the speed of we have more dispersion velocity than thin disk. So the conclusion here is that thick disk plus thin disk works better than thin disk.
Oh, that's thin disk only.
Yes, this is only thin
Because
disk.
thick disk doesn't make a big difference. does it?
Sorry?
Thick disk is only 10% max.
Thick disk is
So it's only 10 max. So why would we change the dispersion?
dispersion in the thick disk is higher.
I know. The thick disk itself in mass is very small. Okay, anyways, go ahead.
So I should look at the distribution of the Einstein cluster. So maybe increase the tail of the. So if you have a higher speed, that would increase produce wider distribution for the Einstein cluster time.
Right.
So maybe it comes from here that while the mass of the thick disk is lower, but it makes better fit.
Well, the rate would be increased somewhat by the higher velocity description, the rate of the mass.
Rate of the mass.
The rate of stars crossing close to one.
Yeah, I can understand the geometry. I'm just surprised that it's not one. It's the thin disk only scenario says that the dispersion is 50% higher than what we know.
Well, no, it's peaked from 20 or 30% higher.
It's surprisingly low.
So it's also a line of sight, right? So
Okay. It's possible to realize
we advise people to try to like this thing.
if you pick the duration.
So and this my part. So the summary and conclusion is that Micorlensing is a unique tool to observe the low mass exoplanets few parsec distance from us, and also it is enable us to measure the mass function of the stars, mass function of the planets, and we can use this tool to study the galactic structure, like the density of the disk, bar angle, and dispersion velocity of stars, and also we can study the mass function of stars in the galactic bulge, because there is no other method to measure the mass function of stars in the bulge. So the gravitational microlensing can work here. And we have a large number of the microlensing candidates towards the galactic bulge, and we can measure the mass function by studying same study that explained here to study the mass function in the bulge. Okay.
Are you thinking Kepler to microlensing, and had that contributed?
Kepler is observing very close by targets, and the optical depth for this is very low. So there's no chance, almost there's no chances.
It's only 350,000 stars, if you think that.
But
It's multiplied up to 10%.
it shouldn't be background stuff.
It's not bounding. It's not bounding.
Okay, the rates you mentioned, like 10 to the minus 6 probability, but how many in absolute numbers, how many events do you have actually?
So for the LMC, it's about 10 events. For the spiral arms, 22 events. And for the bulge, which is, we have very dense field, annual microlensing candles is about 1,000, which is used for exoplanet observations. But now nobody looks to the spiral arm because everybody concentrates to the ball of the exoplanet.
Do you have more Gaussian in the model?
Yes. Yeah.
Any question that can Sohrab again?